Hello, it's great to be here. I'm Michał Michalik, and together with Arek Kobalewski, we are Linux device driver engineers at Intel. We are also maintainers of open source application called Synce4l, and we would love to tell you something about it in this presentation. At the very beginning, we'll introduce some very basic concepts about why we need time, phase, and frequency synchronization. Then we will talk very briefly about PTP protocol and Synchronous Ethernet. After that, we would introduce Synce4l, focusing on application overview, give you some implementation examples, and introduce the requirements. After that, we would shed some light on recent changes and alignment to the new DPL kernel subsystem. Then we will tell you something about the application configuration, finishing our talk with the future of the Synce4l project. Okay, so let's start with why we need synchronization in the first place. Nowadays, more and more traffic is being pushed through mobile networks. The report prepared by Cisco estimates this mobile traffic in 2022 to be almost a quarter of the whole volume of the internet data. Such a traffic creates a demand for high data rates and continuous development of telecommunication standards and technologies, especially when we are talking about the 5G and upcoming 6G networks. So what is so different from the previous generations that we require better and better synchronization? 4G in most of the real-life implementation uses frequency division multiplexing. That means that the uplink and downlink are being transmitted in different channels or bands. Next generations of networks lean more and more towards time division multiplexing, which means that the uplink and downlink use the same bandwidth and the time is split between the two. It is presented in the image on the right. So in other words, at each moment in time, either uplink or downlink has the full bandwidth available just for itself. Such approach allows to more flexible assignment of the available resources depending on the needs. The requirement of frequency stability is exactly the same between the TDM and FDM as it's presented in the table, which is plus minus 6 parts per billion. It is not the case for the phase and time requirements. Those are quite different for the TDM and FDM. So the 5G TDM requires the phase and time to be synchronized to plus minus 1.5 microseconds. And the next generation mobile networks will also be extensively using technology called carrier aggregation. Very shortly, like, what is carrier aggregation? Carrier aggregation allows us to use multiple channels in single connection. When all the channels are contained in single band, we call it intra-band carrier aggregation. In all other cases where the carriers are parts of separated bands, we call it interband. The difference is presented in the image to the right. In such scenarios, the requirement even more strict and can be as low as relative 130 nanoseconds. Those numbers are actually quite important, so please keep them in mind because we'll be returning to them in a second. Natural question which comes to mind after seeing those numbers is what happens when we fail to satisfy them. So the most important consequences are call interference, poor call quality, dropped calls, problems with handovers, decreased efficiency of bandwidth utilization, poor signal quality on the edge of a cell, interference between the cells, and lost packets in data transmission. So how to make sure that we actually satisfy those requirements? one of possible solutions is having GNSS like GPS or similar installed at each node. Unfortunately, that brings very high cost of installation and maintenance. Additionally, it is prone to signal loss and jamming. There is more practical solution. It is a kind of a hybrid approach. So we are using the global navigation satellite system in some nodes as a good clock reference, and then use PTP plus SyncE as a clock distribution. I will talk about those two protocols next. PTP is a protocol defined by IEEE 1588 and allows precise synchronization of time of a day, phase, and frequency over network. We won't go into too many details because the topic has been well covered by our colleague Maciej Machnikowski in the last two Netdev conferences. If you're interested, we are leaving the links below. The most important information for us is that PTP can achieve sub-microsecond accuracy in the best case scenario. As we remember, it is not enough for carrier aggregation application in 5G networks. So how precision time protocol works? In general, PTP followers communicate and exchange information with leader through Ethernet network. PTP follower can do two actions to synchronize the hardware clocks. First action is that they can actually set the values of the clock directly, and second action is to actually to adjust the frequency of the clock by tweaking the increment value in here. This increment value is added to the PHC at each tick of the internal clock, and as you can see, since we are talking about each tick of the internal clock, the clock quality is very important to having good frequency synchronization. Because if the internal clock is drifting up, so the frequency increases, the PTP need to react and actually lower the increment value, which would be added to the PHC hardware clock. If the internal clock is slowing down due to instability, the PTP would be reacting with increasing the clock, and so on and so forth. The biggest the drift of the clock, the biggest reaction on the increment value, which leads to not very good frequency synchronization, which leads to the lower quality of the time of a day and phase synchronization of the PTP hardware clock. So we need to have a possibility to somehow make sure that this desired frequency is quite stable. So how can we achieve that? Solution to this problem is using Synchronous Ethernet to stabilize those clocks. This protocol can calculate the best clock source and recover from that link, and actually synchronize and feed it back again to the system. It needs special hardware which is called DPLL, but more on that a little bit later. Such a hybrid system with some improvement to the PTP can achieve sub-nanosecond synchronization. The White Rabbit project it's a good example of such implementation. So to sum up, Synchronous Ethernet is a protocol defined in a set of ITU-T standards allowing transferring of clock signals over Ethernet physical layer. To achieve that, network interface cards needs to have an additional logic allowing clock recovery and possibility to recreate the signal and feed to all other devices. The SyncE signaling is sent on layer 2 of the OSI model. The recommendations which define the SyncE are ITUT recommendation G.8261. You can find the architecture and wonder performance of the SyncE networks. G.8262, which specifies the clock for SyncE, and G.8264, specification of Ethernet synchronization messaging channel, in short ESMC. And the last one is most interesting for us because it actually describes the logic of the SyncE4l application, and we will talk more about that in a second. As mentioned earlier, there are some system requirements to enable the SyncE. First, there are some special hardware requirements. So the network interface card needs to be able to recover this clock signal from the Ethernet PHYs and feed it back to other PHYs. And also we need to be able to read the state of the internal DPLL. There is also a software requirement to be able to understand which port is the best to choose the clock recovery. SyncE need to know the quality of the clock which drives this link on the other side of the wire. So some kind of synchronization protocol is needed. And here comes the Synce4l project. Synce4l is hardware agnostic open source implementation of synchronous Ethernet synchronization according to mentioned ITUT recommendation. Application is providing logic to SyncE enabled hardware by processing ESMC frames and controlling Ethernet equipment clock on network interface card. You can find the project using the link below. ESMC is Ethernet slow protocol specified to carry the information about clock quality on receiving link. It is organization-specific slow protocol standardized by common efforts of ITUT and IEEE. Protocol distributes clock quality information through Ethernet link. More details on the protocol itself was shown 2 years ago on the Netdev presentation, and I'm leaving you the link below if you are interested in the implementation specifics of this particular protocol. On the next slide, my friend Arek Kubalewski would present you the features and the principles of Synce4l application. Arek, the floor is yours.
Thanks, Michał, especially for explaining all the hard parts. And hi Netdev, my name is Arkadiusz, a software engineer at Intel, mainly focused on time-sync domain of networking products. Here I'm trying to explain what Synce4l application actually can. So, let's start. Our initial idea was to have Synce4l as an additional application in the Linux PTP project. But thanks to the community review after we submitted it, turned out to become a standalone project available at GitHub, although the parts of Linux PTP code are still there. It is not a user-friendly application. It is not because it's a user-friendly daemon. Basically run it and forget about it. Works in the background while producing traces mostly on critical events, unless debug log level was configured, in which case all the events are traced. For now, it's only configurable with the config file at startup, so the user is not able to change any configuration dynamically. Also, worth to mention that a single configuration file might contain multiple separated EEC devices configured and running. Also, as it requires access to the raw sockets and configures hardware, the one needs to execute with sudo. But how it actually works? In the most simple example, there is only one leader and the peer followers. As the followers would recover clock from PHY medium, they must be physically connected, so unlike the PTP, SyncE functionality works only for directly connected peers. In this example, the leader has configured external source, for example SMA with QL value of PRC, as well as number of network ports which are connected with the followers. Once signal hits DPLL, it starts the lock procedure. DPL becomes locked and SyncE-forl starts sending ESMC frames to the followers. The quality level of the leader is propagated. The followers SyncE-forl starts lock procedure to the clock signal recovered from the ports. And once followers locks with the leader signal, it starts sending do not use QL back to the port they are synchronized with. Here is a continuation of the first example, but we extend the network with two additional peers connected with the followers from the previous case. All procedure starts the same as in the first example. So the clock signal goes to the DPLL, DPLL becomes locked, QL PRC is propagated to the followers, their DPLL is getting locked, they start sending do not use, and PRC to the other ports configured. In which case, another layer of followers would do exactly the same. So their DPLL becomes locked, and they start sending do not use back to the follower. And now, let's complicate things a bit. Here we add another leader with better quality signal than previous leader. So the left side is actually the same as it was in example 2, and synchronization followers would send QL PRC to the synchronization leader. In this case, he is not yet locked, so he is still sending do not use. But once the signal is getting to his DPLL and he becomes locked, he starts sending better QL back to the followers. So they must react, in which case their DPL first becomes unlocked, then locks with the new QL with the port received from the new leader. They start sending back QL do not use back to him and start sending QL ePRTC to the other ports configured. And this continues. So first DPLL becomes unlocked, QL do not use is propagated to the other ports, DPL becomes locked, it starts sending QL PRTC to all the ports that are also configured for this SyncE-forl daemon. Then even our previous leader finds out that this signal is better quality than his own, so he also needs to follow the procedure. Eventually he becomes locked, he sends do not use back to the ports from which he is now synchronized, and then sends QL PRTC to the last follower in the network. So he also becomes locked. EEC synchronization is done with the use of a DPLL circuit. As we couldn't rely on the vendor or hardware specific solution and there was a need for common API, we worked for over a year with the community on introduction of DPLL interface to the Linux kernel. A common interface that would allow control over DPLL and whose EEC is able to be controlled. DPLL interface allows for control over DPL devices and their pins, as well as status reporting. Interface is based on the generic netlink and has built-in notifications about status changes. The latest version of SyncE, which is 1.0.0, was produced and is also based for this presentation. It introduced two major features: unified approach to the sources. In previous versions, SyncE4l acted explicitly as an external source-based leader or as a line source-based leader or follower. Now the sources can be mixed type of a single SyncE device. Also, support for Linux DPL subsystem was added. It allows to control the EEC device through the kernel interface. It was recently merged into NetNext 3, but we are still waiting for merge into 6.7 Linux 3. There are two work modes of SyncE4l. One, legacy, where Linux system commands are invoked to control EEC. Commands are provided by the user within the config file. and DPLL mode, where Linux DPLL subsystem is used to control EEC. Currently it works only with automatic mode, DPLL, and the config file requires config items which would identify the DPLL device and pins related to the configured EEC inputs. Now, let's try some configuration. The configuration file is made up from three section types: global, device, and sources associated with the device. Any new section is denoted with the square bracket. Device has additional triangle bracket, and external source has additional curly bracket. Line source is a network port capable of recovering signal from an active link with the neighbor peer. External source is an external clock signal provided from external device, in example through SMA, or provided with a source embedded into the board, like a GNSS receiver. Global section consists of items that would affect SyncE runtime globally. Right now, these are only related to the tracing and their configuration. The one could configure logging level, where 7 is the highest debug log level, and for normal operation 6 is recommended. Enable tracing to syslog. Being verbose means traces are directed to the standard output. Message tag allows custom trace tag, which is useful when tracing to syslog to filter SyncE-forl related traces. Here are two examples of configured devices. Extended TLV and network options are configurable as per SyncE specification, but recovery time was added for testing purposes. The configuration items and their default values are described in the README file and sample configuration file in the SyncE4l repository. On the left we can see a device configured for legacy mode support, where a Linux command is provided by the user to inquire hardware EEC log state. Also, possible return values of getState command are defined by the user. On the right, the configured device with support for DPLL subsystem, where the clock ID is EEC clock ID, module name of kernel module name which has registered the DPL device. As for now, there is only support for automatic mode DPLL. The user might need to provide the do not use priority value for inputs, which would be set on all the inputs of EEC type DPLL device targeted by SyncE4l in runtime. Basically, all the sources which were not configured for SyncE but exist on DPL device would be set with do not use priority. Here is example of few devices in the config file. Basically, each device is followed by the number of sources, or the sources below the given device are belonging to that device. Then the second device can be placed also with following sources. Here is a slide with a number of sources configured with legacy mode. Each source needs to be given two system commands: one to enable the source, second to disable it. For the line sources, the user can also configure the RX or TX heartbeats, but default values shall be good enough to meet SyncE specification, so they can be left blank like on the second example. Third source is external and must be configured with a QL value, also with extended QL value if the device was configured for extended TLV support. Here are sources configured for DPLL mode. And the name of line source would be associated with the DPLL pin, so it is enough to have the source in a square bracket under the corresponding EEC DPL device to have it configured. External sources are similar. The user needs to provide one of the labels which would identify the pin associated with the EEC DPL device. In this example, board label is enough. As for further development plans, we need to introduce the ability to change configuration on SyncE-forl runtime, as this is required, for example, in automation of changing the quality level of input signal provided to SMA source. Introduce ability to change multiple DPL devices in the one system, as well as introduce support for DPL working in a manual mode. Yeah, and hopefully we still have a few minutes for some questions.
Two questions. The first one, have you spent any thought on how this would work for routers or switches with more than one port, and especially when you have more complicated topologies of how the clock can be distributed in the system, like how that would be expressed from the hardware config, so you can actually work with it? And like, are you looking at that, or are you just looking at end device support?
Yeah, maybe the first part is about the switches. Yeah, this is designed to work with multiple ports, right? So it's not a problem to run it with, I don't know, 16, 32, whatever ports. You just need to like give this config items in the config file, and this should work. But it's strongly like behaving depends on the hardware, right? Because without the hardware it supports it, SyncE-forl doesn't work. So you need the hardware, you need hardware DPLLs and availability to like recover the clock from the given port for each port you are configuring.
Okay, so you can already have one port as an upstream clock port, and then multiple downstream clock ports with other devices connected. Okay, that wasn't clear to me. Sorry. And the other question for me, just to understand this correctly, with SyncE, you'd only get the rate of the clock, so you still need PTP to establish the phase? Or is that a wrong assumption?
Yeah, I mean, you with SyncE, you're only synchronizing your clock to the neighbor peer, right? So if the neighbor peer is giving you the frequency, you can recover it from the Ethernet signal, and your network card would tick with the same clock, with the same ticks, right?
Okay, so the user space component interacts with the PTP code, or like do you need to run both the SyncE daemon and the PTP daemon in the Ender setup?
Well, let me jump in, Arek, if you don't mind. It is like connected because it depends on what you want to achieve. The SyncE actually allow you to only get the frequency synchronization. For example, if you need to synchronize the time of a day or a phase, you still need to something else. For example, PTP in this case. But what you can do, you can stabilize those clocks with which powers the PHC. Which basically like works as a source for it. You can use SyncE to actually achieve that. So depending on the needs.
Yeah, basically SyncE helps you to like keep this good time of your machine, right? So once it's synchronized, you can have either with the first like example SyncE only, you are getting only clock synchronized, so you should always be able to communicate with your neighbor. At least there won't be any clock skew of the microchips on your board, so they should always communicate. And this, if the signal is good quality, you would never most probably you would never need to change the time, because it would be all working together.
Yeah, I think we're doing well on time. AV is getting better, guys, right? Last day, we finally figured everything out. Hello back. Okay, any more questions online? Any questions online? No. Okay, let's thank our speakers, please.
Yeah, thank you.